Hello guys, welcome back. This is the second session for week 8. Right, so on Friday we have been discussing about Riemann sums and how to compute the Riemann integrals. And then we, as limit n tends to infinite, or if I increase the number of rectangles, we said it will approach to the exact area under the curve between the point A and point B. Right, so that can be represented and denoted as integral a to b f of x dx, which is exactly captures the area under the curve of a function f of x from a to b. Right, so we ended our discussion here, and once we define this definite integral, there are some properties to it. Right, so if you have two functions f1x and f2x, right, and you want the area under the curve of the sum function f1x plus f2x from a to b, you can actually write it as you compute the area under the first curve plus you compute the area under the second curve, which will give you the total area under the summed up function. Right, so this you can prove it graphically also. You just plot two functions and you also plot the third function, which is the sum of these two functions, and see how the area of the third function connected to the first two functions. Okay, so you can prove that easily. I'm leaving that proof for you guys. Okay, and if it is minus, okay, if you are looking for the difference of these two, here also it will just be the difference. Okay, and if you have some scaled function like c times, if our function is scaled by c units, and you are looking the area under the curve from a to b of the scaled function c times f of x dx, you can actually pull out that c, constant c, outside of this integral, and you can write it as c times integral a to b f of x dx. So this also graphically, if you look at the graph version of this, it makes quick sense. Okay, so you can plot f of x, take a function f of x and take some value c to it, like you just take twice of f of x and see how the curve shifts, and then you will get a sense that the connection between the scaled function c times f of x, area under its curve, and the function itself, area under the curve, it will just be c times of it. Okay, and this also you can prove graphically. And the next property is you can actually split the integral. If you have some point in between, say d, now if you want to compute the area under the curve from a to b, you can do it in two steps. You can compute the area from a to d and compute the area from d to b, and then you add both the areas, which will be equals to the total area. So this also graphically you can get an intuition. And maybe I will draw it for this. If you have some curve from say a to b, and you have some other point in between d, right? So you want the total area, which is this orange thing, right? Total area under the curve from point A to point B. This is the total area. So you can compute this total area by computing this area first, right? From A to D, you compute this area, and then you compute this area from D to B, right? And then add the green and gray regions to get the whole orange region, right? So that is what this property says. And last property is, if you have two functions, one function is always lesser than some other function in the interval a to b, then area under the curve will also be lesser. You can compare the areas also. So this also, you just take two functions, right? So let's say this is g of x and this is f of x. So f of x is lesser than g of x in this interval a to b. So you can clearly see the area under this orange curve, right, is lesser than the area under the red curve, right? So these are some nice properties that we can use to compute the integrals of other functions, or you can bound the integrals. So you can use this last property to bound integrals. Okay. So that is one thing. And the next thing is, if the function, the integrand, so which is inside the integral, if it is having some special properties, then computing integrals are much easier. So we have some nice equations and properties of this function we can use and further reduce the computation part, right? So these properties will help us to reduce the computation part. So you don't have to blindly compute area under the curve from starting from point A to point B. Okay, so let's see that. For suppose if f of x is even function, we all know what an even function is. F of minus x is equals to f of x, right? Or graphically, it should be symmetric along y-axis, right? So if it is symmetric along y-axis, then if you want to compute from, let's say, some point A to point B where A and B are positive values. Okay, so here in the graph you can see A and B are positive side, and you want this area, and that area will be equal to the area from minus B to minus A, right? Because it is symmetric, right? So the green this region and this region will have the same area if it is even. Here f of x is even, and we will use this one to compute these kind of expressions. Let's say you want to compute from minus a to plus a, right? You want this area. So should I do from minus a to plus a directly, or is there any easy way which I can reduce this minus sign? Okay, so minus always gets confusing, right? And also it is the lower limit. So when we discuss about this fundamental theorem of calculus, we'll see that this creates some, when lower limit has a minus inside it, this may create some confusion. But if f of x is even, all we can do is we can clearly see from minus a to plus a, from minus a to 0 and 0 to a, both have the same area because of the symmetriness of the function, right? So rather than computing the whole area, I will just compute this area and take twice of it, right? So just add it once again. That will give me the total area from minus a to plus a. And this is one important property, you can call it, that we can use to reduce the complexity of computation, right? So that is one. This is with respect to if f of x is even. What if f of x is an odd function? Right? So odd function is f of minus x is actually equals to minus f of x, right? Or graphically we say it is symmetric along origin. So from origin, if you move this side, you have to move exactly opposite to it. So it will be symmetric about origin, right? So if f of x is odd function, then we have this nice property. If I integrate from a to b, f of x, that will be equals to minus of integral minus b to minus a f of x dx. Here also this green region and blue region have the same area, but the green region is on the negative side and blue region is on the positive side, right? And here comes the most beautiful property we can say, right? If f of x is odd and you are trying to integrate from minus a to plus a, some real value a, okay? If you know that f of x is odd, then you can clearly see that this area and this area both are equal, but one is on above x-axis and one is on the below x-axis. So both will get cancelled out and the result will be 0. Right, so nice result to cherish. Right, so these are some properties that we can use to reduce, as I said, to reduce the complexity in solving. Okay, so we'll do quickly couple of problems to feel the properties. Okay, so to get the sense of the properties. Okay, so here I have given from -3 to +3 x cube plus x power 5 dx. Okay, so even if you don't know what is integral of x dx, right, from some point A to B, even if you don't know this, we can do the first problem. Right, how? Okay, what is the answer to this?
0.
0, sir.
Yeah, it's straight away 0. You don't have to know any uh, pairs, integral pairs. You don't even have to know what is integral of x. All you have to check is this is going from -3 to +3 and check what kind of function is x cube plus x power 5. This is an odd function. Right, so if the integrand is odd and you are integrating it from -a to +a, so the result will be 0. Right, no computation, nothing, one step done. All right, so what about this? Okay, take a minute or two, try to solve this.
It's 2. Sorry, sir. It's 4.
Okay, so option A is 4. Let me wait for 1 minute at least. Okay. Okay, let me tell you, this problem should not take more than a minute for you guys. Okay, so you have to get such good understanding on these properties. Okay, and my suggestion is whenever you see these kind of integrals, no, don't rush to go behind doing the knowing the antiderivatives of this and then take the antiderivative, substitute the limits. Don't go in the hard way. Just look out for these properties and check whether those properties help you or not. If properties helps you, the problem will be solved in minutes, at max 2 minutes. Yeah, Nitish.
4, 4, sir.
4. Okay, so you also say 4. Any other answers from anyone? Okay, so let's do this. So if you look this combinedly, x cube plus mod x is neither even nor odd. Correct? But what we can do is, this we have discussed, right? It is sum of two functions. X cube is one function, mod x is another function. So what I can do, I can use that sum function property, right? So I can split this integral from -2 to 2 x cube dx plus -2 to 2 mod x dx. And if you look at the first integral, this will be straight away 0. Because again, I'm trying to integrate from -2 to 2 x cube dx, and x cube is an odd function. So odd function integrating from -a to a, straight away 0. And coming here, how will mod x is? Mod
Mod
x is
x is a even function.
an even function. And again, we know this property that if the integrand is even, all I can simply do integral 0 to 2. And in this integral, in this interval, mod x is actually x, right? So even if you write mod x dx, or you don't need to write mod, right? So it will behave like x. Even if you plot also, you will understand that, right? So now we were down to just knowing the antiderivative of x. And the antiderivative of x is
X square by 2.
x square by 2. And the limits are 2 and 0. If you substitute the limits,
We
you will
get
get
4.
2 into 2, 4. As simple as that. You see, it should not take more than a minute if you go by using properties. But if you forgot the properties, then integrating mod x is an issue, right? And also for if you sit and solving for x power 4 by 4 and then substitute the limit 2 and minus 2, it will take 2 more steps. Like you'll waste some 30 seconds or maybe even a minute there, right? And every minute is crucial during the exam. So please be very mindful about that. Okay, so these are a couple of examples that actually makes
Sir, can we generalize
us.
the statement? Can we generalize the statement, and if we add two functions, first even function and second odd function, then we will get the neither odd function or not even function.
Yeah, that is how it is, no?
So we can generalize it.
You can generalize it because if you have f of x plus g of x, where f of x is even and g of x is odd, right? So now if you treat this as h of x, then you compute h of minus x, which is f of minus x plus g of minus x, which is, since f of x is even, f of minus x will be f of x. If g of x is odd, g of minus x will be minus g of x. And this is not equals to h of x.
HS.
And similarly, this is not equals to
Minus of HS
minus h
minus
of
x.
x. And so therefore, you can imply that h of x is neither even nor odd. So these are very nice, beautiful two-step proofs, right? So maybe this is how I fell to math. Maybe you can also try, and maybe one day you will also start liking math. Okay. All right. So let's come to the most important theorem for calculus, and also very basic theorem that we all should learn. I hope we would have seen this in class 11 or 12, but we don't know what exactly is that, right? So, which is called fundamental theorem of calculus. From the term itself, you can say this is very, very fundamental. That means very basic theorem that we all should know. We would have used this, but we don't know what the theorem is, right? So, what this theorem states is, if we have some function which is integrable in the interval a to b. So integrable means it is nice, smooth, and there is some area under the curve, right? And if there is a function f, capital F, which is differentiable. Okay, so small f is integrable, capital F is differentiable in the same interval AB, such that if I take the derivative of capital F, I should get small f. If I have these two pair, capital F and small f, then what fundamental theorem of calculus states is, if I am computing the area under the curve of f of x from a to b, which is integral a to b f of x dx, is actually equals to f of capital F of b minus capital F of a, right? And to our surprise, we have already used this just before, right? So that is there, but yeah, so this is the theorem. Where we used here integral of 0 to 2 x dx. What we did is, we have this x, which is small f, right? And the corresponding capital F will be x square by 2, because when you take the derivative of x square by 2, it will be 2x by x, 2x by 2, and it will be x, right? So, and this is small f. So we have a pair, capital F prime and small f, both are equal, and therefore this will be capital F of 2 minus capital F of 0, which is capital F of 2 is 2 square by 2 minus capital F of 0 is 0 square by 2, which we got 2, and we multiplied it by 2 because outside there is 2, and finally we got 4. Okay, and this capital F is called the antiderivative, right? So it's opposite of derivative, kind of, right? So when I take the derivative of the capital F, I will get small f. So if I do the antiness of derivative, I will get capital F. That is called antiderivative, and it is denoted as, not equals to, it is denoted as a f of x. So which is like antiderivative of the function f of x. Okay, so we'll, yeah, I know this is very easy, but let us all go through it to bring everybody on to the same page. Okay, so we have many pairs which are very easy, right? So let's put it in a table. Okay, so here the first column we will write the function f, and here we write its antiderivative. Antiderivative a f x. Okay, so here it is function f. Okay, all right. So the very first one is simple. We all know if the function is just the constant, its antiderivative will be ax plus c, right? And I forgot one thing, and these antiderivatives are not unique. So derivatives are unique, right? So if given a function to you, if you compute the derivative of that function, that will give us another function which is unique. But whereas antiderivatives may not be unique. When I take the antiderivative, f is equivalent to f plus some constant c, because when I take the derivative of this constant c, it will just become 0, right? So f and f plus c have the same derivative function. So that is why antiderivatives are not unique. So this is the reason why we write plus c. Okay, so when you do integrals, we usually write the constant, right? Integral constant. So that this is the reason. Okay, so let's come back. This is constant function, and the next function is x power a. Okay, so power functions or polynomials. Okay, and this is x power a plus 1 divided by a plus 1 plus c, and the c's are just the constants. Okay, and yeah, here if you observe, a plus 1 is in the denominator. So one strong note that a should not be equals to minus 1. And we will see what happens if a is minus 1. Right? If a is minus 1, it will be 1 by x. And we'll see what will be the integral of 1 by x. Or maybe within a week. Okay, so it will give rise to a new function which is called logarithmic function. Okay, so that is there. But apart from a being minus 1, if it is anything else, this will be the antiderivative. Okay, and once we know these powers, polynomial we can write it easily, right? So if I have some some p naught plus p1x plus p2x square plus and so on, pn x bar n. So if this is the function, its antiderivative is, I can actually compute each term, its antiderivative, and just add it. So it has a nice property, and we'll use that, and you can write this as p naught x plus p1 x square by 2 plus p2 x cube by 3 and so on, pn x bar n plus 1 by n plus 1, and don't forget plus c. Okay, so this will be the antiderivative for the polynomial. And next comes the exponential, which we learned last week. Right, so if you have some general exponential like e power ax, this will be e power ax by a plus c. Again, the denominator should not be 0. That is an extra condition. And you can clearly see, right, if a is 0, e power 0 is 1. And we know e power 1 is a constant function. It will not be an exponential function. Right, so these are some standard antiderivatives. Okay, so I hope no doubts. If at all you have any doubts, you can ask. Okay, so let's do some problems. Okay, so real quick. So we'll combine this even functions. We'll combine this antiderivative computation, everything together, and let's solve more problems. Okay, let's start with the very first problem like this. Okay, so something like this. Okay, so even I am not sure what the answer will be. I think professor has done this in the lectures. You can take back a look, take at it, take a look at it. And okay, let's try to solve this with all the knowledge that we have gained so far. Okay, so firstly, let's try to plot this so that we'll understand what kind of function is this x square minus x minus 2 absolute value. Right, so let's factorize it first. X square minus x minus 2 can be factorized as x square minus 2x plus x minus 2. So it can be factorized as x plus 1 into x minus 2. Right, so this is a quadratic function and roots are minus 1 and 2. If I roughly plot this, and it's the power, the coefficient of x square is positive, so it will be an upward parabola and it will intersect x-axis at minus 1 and then 2. Right, so roughly this is how it will be. This is minus 1 and this is 2. Now if I take the modulus of this, what do you think, or how do you think the curve will change?
Curve will be fold within the radius of 1
Sorry. So when I take the modulus, what happens is, if it is positive, it will stay positive. If it is negative, it will become positive. Right, so this red curve, if you see the red curve, left of minus 1 and right of 2, the function is positive only. So it will not change. Even if you take modulus, it will not change. Whereas from minus 1 to 2, the function is negative. X square minus x minus 2 value becomes negative. When I take the absolute value, it becomes positive. So that means it will, within the interval -1 to 2, it will have a mirror image to the red curve. Right? So this is how the curve will be. This will be positive itself till here. Later it will just have this kind of shape, and it will go like this. Some W kind of shape. Right? So do everybody agree to this?
Yes, sir.
This is
Yes.
the modulus x square minus x minus 2. Now what do we want? We want area under the curve of this function from -3 to +3. And -3 will be somewhere here. +3 will be somewhere here. Right? So this is how it is. This we know. From -3 to -1, the function is same. X square minus x minus 2. And from 2 to 3 also, the function is x square minus x minus 2. But within -1 to 2, it's not x square minus x minus 2. Rather, it will be negative of this. Right? So, because x square minus x minus 2 is negative, if I take negative of negative, it will become positive. So, within this, it will be minus x square plus x plus 2. So, what we will do? We know for computing the total area, we can compute it in intervals. So we'll compute this area first and this area separately. Right? So we'll compute these two areas separately and also this area separately. Right? And then I will just add this, all three areas. So that is the plan. So firstly, I will split this integral into -3 to -1. Let's come to that dx, and then -1 to 2 dx and 2 to 3 dx. Right, so from -3 to -1, it is simply x square minus x minus 2. Function is not changing, it is positive anyway. We will keep it as it is. Whereas from -1 to 2, the function is changing to minus x square minus x minus 2. Sorry, minus x square plus x plus 2. And from 2 to 3, it is becoming x. It is x square minus x minus 2. Alright, so now we have nice expressions. So we know the antiderivative of x square. We know the antiderivative of x. We know the antiderivative of the constant too. Right? And we know the fundamental theorem of calculus also. All we have to do is use all of them together. So x square minus x minus 2's antiderivative will be, it's a polynomial. So x cube by 3 minus x square by 2 minus 2x. Right? And remember, I'm not writing plus c here. Right? Because no need. That is what fundamental theorem of calculus said, right? So we don't need, even if you write plus c, it will just cancel out on both sides. So you don't have to write plus c. But what you have to be very, very, very careful is when you substitute the limits. Okay, I will do one part and maybe the next two parts you can compute by yourself later, and then you can post it in the G spaces or discourse. Okay, so now the upper limit is -1. I'll take capital. This is simply f of -1 minus f capital F of -3. Right? So there is minus here. So that we have to be really careful. So f of -1 is -1 cube by 3 minus -1 square by 2 minus 2 into -1. This is f of -1. And then there is minus. And f of -3 is -3 whole cube by 3 minus -3 whole square by 2 minus 2 times -3 is the lower limit. Well, now if you simplify, you will get -1 by 3, -1 whole cube by 3 is -1 by 3. And then we have -12. Right, and then we have +2. And on the other side, there is minus still here. This is minus 3 whole cube is minus 27 divided by 3 is minus 9. And then minus 3 whole square is 9, 9 by 2. And then minus 2 times minus 3 is plus 6. Right? If you want to evaluate this and this separately and they take the minus, or you can combine all of them together. Both works. So this will just simply be minus 1 by 3, minus 1 by 2, plus 2, plus 9, plus 9 by 2, minus 6. Right? So this also you can compute from. Similarly, you compute this, and add all three values, you'll get the final answer. Okay, I hope you guys can do that. But this is how you should do. Okay, so do not be in a hurry and do not rush. That is what I wanted to say. And don't get frightened by looking at these expressions. Okay, so if you can plot them, roughly plot them, if you have gained the skill, then do a rough plot and then do step by step. Even if you lose 3 minutes of solving this, it's fine. You take the 3-4 minutes and solve it. Rather than rushing things in minute or two and getting a wrong answer, it's good to spend 3 minutes and get a correct answer. Okay, so that is one thing. Even I'm not sure. I didn't compute. Maybe you guys can have another discussion on this in the space. Okay. All right. So the next thing is there are some techniques, integration techniques. Okay. So far we know only the integrals of these 4 functions. But even if the functions are little complicated, looking complicated, if they have some nice behavior, we can use some techniques and compute those integrals. Okay. And this mainly we focus on 2 techniques. One is called integration by substitution. Okay. And another one is called integration by parts. Okay. So in this integration by substitution, right? So what we do is the integrand, the inside function may look little complicated or little outside what we have learned, right? But if we do some substitution, variable change. Okay. So if we bring in new variable into the integrand, then it will boil down to a very well-known function. Okay, so that is the technique that we are going to use and solve these integrals. Okay, so this is like we bring in a new variable v, maybe v or u or v, which is a function of x. Okay, so instead of x, we will bring in some other variable v. All right, so that by bringing in that variable, our complicated function boils down to the very well-known function. That is integration by substitution. And integration by parts is like if you have complicated like multiplication of 2 functions, right? So you have product of 2 functions, and what we do is we do integration by parts. Just like when you have product of 2 functions and you want to compute the derivative, what we did the derivative of the first function times the second function plus the first function into the derivative of the second function. We did it in parts, right? So we took the derivative for the first function one time and then we took the derivative for the second function second time. So here also we will do it like that. So we will write the given inside integrand into 2 functions. We divide it into 2 functions. Again, you can divide it as f of x as some u of x into v of x. Right, so instead of f of x, we treat it as u of x and v of x. And then we use this particular technique called integration by parts and write this u of x into v of x as some nice way so that we can compute the integrals. Okay, we don't need this u of x into v of x. Rather, we just need to know how to integrate v of x separately, how to differentiate u of x and its multiplication with v of x. Okay, so that we will see. But these are the ideas behind these techniques. Okay, we'll see one by one. Okay, so let's start with integration by parts. Sorry, by substitution. And this integration by substitution, we cannot use it for any f of x. Okay, so it should be in good format or required format. And the format is something like this. So if I have my integrand, this f of x, okay, as, if I can write this f of x as some function, composite function g of u of x into its inside function's derivative. Right, so if I can write f of x in this fashion, so I will write f of x as some other composite function g of u of x and u of x derivative product. Okay, if I can write f of x like that, then what I will do is I will do substitution. So I will bring in our new variable v as u of x. So by bringing this v as u of x, what happens is if I take the derivative of v, it will be u prime of x dx. This is dv, right? V prime or dv, right? So if I take the derivative, I'll have dv to be u prime of x dx, right? So now what happened? This will just boil down to integral a to b g of v, and this, you see this u prime of x, you can replace it with dv. Now if you don't know f of x dx, right, if f of x dx is not in our standard form, and if we can, but we know what the integral of g of x function is, and if you can able to write our f of x in this particular fashion, it will boil down to this integral, and we know how to integrate g of x dx. We know how to integrate g of v dv. Okay, so let's do an example, then we'll understand it. Okay, so let's say we want to find the integral of 1 to 2 e power minus 1 by x divided by x square dx. Okay, so right now we don't know the techniques how to integrate this function, which is e power minus 1 by x divided by x square. But I want to find some g of x, which I know the antiderivative, and some u of x such that I can write this e power minus 1 by x square as g of u of x into u prime of x. So I need to find g of x, u of x such that this happens. Can we find this? Is it very easy to see? Anybody? U of x is
1 by x.
U of x. You can take it as 1 by x or minus 1 by x.
minus 1 by
Minus 1 by x. Yes, sir.
Minus 1 by x. So when you take u of x to be minus 1 by x, then you will see that u of x is minus 1 by x and u prime of x is 1 by x
1
square.
by
1
x
by x
square.
Right, so x power minus 1's derivative is 1 by x square. So now what we have something like e power u of x divided by, e power u of x into u prime of x. Now from this, can we say or see what is g of x? So this is e power minus 1 by x divided by x square. Now we have written it as e power u of x into u prime of x, and this should be g of u of x into u prime of x. Now from here you can clearly see that g of u of x is e power. From here you can see that g of u of x is e power u of x. Correct. What will be g of x?
E power x.
E power x. That's it. No. So you have u of x that came in the power. When you simply have x instead of u of x, all you have to do is right side also you will replace u of x by x. That's it. Once we got this g of x as this and u of x as this, and we know that g of u of x into u prime of x is e power minus 1 by x divided by x square. Now this will simply be integral from 1 to 2. Right. So what substitution should I make? I should bring in some variable v, which is u of x. Right. So this is the substitution I will make. And once the substitution is made, we can clearly see this is e power v into, now 1 by x square into dx. Once v is u of x, that means if I take the derivative, dv will be u prime of x. U prime of x is 1 by x square dx. Right. So if I do the substitution, I will get e power v into this 1 by x square dx will simply be dv. And we know how to integrate e power v dv. Right. So this will simply be
Sir, limit will also
The
change.
limit value will also change.
correct. So limit values will also
Yes,
get
it
changed
will
because
become
we are
from. So when x is 1, v will be minus 1, and when x is 2, v will be minus 1 by 2.
correct. So I completely forgot about it. So when we do the substitutions, we make sure that even the limits are properly substituted. Okay, so even the limit values will change. Right. So for that, how we compute them is, along with this dv computation, what we have to do is, these are x limits. Right. So 2 and 1 are x limits, and we know v is minus 1 by x. So when x is 1, its corresponding limit of v will be minus 1. Right. So minus 1 by minus 1 by minus 1. So minus 1 by 1 will be minus 1. And similarly, we have to compute the upper limit. When x is 2, it will be, for v, it will be minus 1 by 2, which is minus half. Right. So therefore, when we substitute, instead of integrating it from 1 to 2, we will integrate it from -1 to -half. Right, so -1 to -half e power v dv. And if you integrate e power v, and again we are just using the fundamental theorem of calculus, e power v's derivative will be e power v, and the limits are -half and -1, and this will be e power -half minus e power -1. Right, so this will be the solution. So even though, observe that even though we don't know the direct antiderivative of this expression, we have used the idea of substitution and we have computed the integral. Okay, so that is integration by substitution. And yeah, if you have any doubts, you can ask.
Sir, we can also skip the part of changing limit when we get the antiderivative of f of x, and then we can replace v with u of x, and then put the limit, same limit previously.
Okay, so you compute the antiderivative and replace
No,
v by
no.
u of x.
Right now we have done it like we change the limits because of the changing of because of substitution. But
Hmm.
we can also skip this part when we get the antiderivative of the function and
Hmm.
replace v with u of x.
U of
Then we
x.
can also,
Yeah,
then we
yeah,
can
yeah.
also then limit goes to 1 to 2 as previous.
Hmm.
So we can do it like,
Yeah, it's the same way, no? You can also do it that way, no? So once you have this e power v as the antiderivative for e power v, all you are saying is I will just go back to e power u of x. I will replace v by u of x back, right? And it will just simply be e power -1 by x. And then the limits are 2 to 1. Even here also we'll get the same thing, no? E power -half minus e power -1. Right, you are correct. Okay, but a good practice is when you try to substitute the new variable, you replace everything. You replace dx as well as the limits. You don't have to come back and substitute. Okay.
yes sir.
Okay, so as requested, we'll do one more example for this antiderivative. Okay, so let's do this. Let's say we have to compute the integral from 0 to 5 t square root t plus 1 dt. Okay, so x is not sacred. So that is what I wanted to mention here. Variable can be anything. So you take x or y or t or v. Okay, so here the variable is t. Okay, and we want to compute this integral. Okay. Uh, okay, so first let us all convince ourselves that the direct antiderivative we don't know. Right. So what we have to do is to come up with g of x, g of t, u of t such that g of u of t into u prime of t gives us t square root t plus 1. Is there anything like that? Can I do this in that way?
Sir, it can be done by part method.
Okay, by parts we didn't discuss it. Can we think of a method? Okay, so we'll come back to this. So I think it's, let's say this is problem 3. Let us do some simple one. Okay, so some 1 plus 5x whole cube dx. Or this is also very easy. Let us complicate our lives a bit. So let's say we have something like 2x minus 1 whole square into and then e power x square minus 3x plus 2 into
2x minus 5.
let's do into x minus 2 dx. Okay, so let's do this. And again, we want g of x and u of x such that g of u of x into u prime of x is actually equals to this x minus 2 into e power x square minus 4x plus 5. All right, so is there any nice substitution that I can think of for u of x?
The
X
polynomial
square
function
minus
x square
4x.
minus 4x plus
4x
5.
plus 5. Yes, sir.
Very good. So u of x, I can take it as x square minus 4x plus 5, because when I compute u prime of x, it will give me 2 times x minus 4, which I can write it as 2 times x minus 4. Sorry, x minus 2. Right, so I have this. I have this e power u of x into u prime of x by 2. So you can pull this 2 to the left side. Right, so all we have is this will come to 0 to 1 e power u of x into u prime of x by 2 into dx. Right, so we have this. Now all we need is, what is g of x? Right, so what is g of x? It will just be e power x again. Right, so then you do the substitution. So let me take this below. Okay, so now what will happen? This will be, from here you can see g of u of x is e power u of x. So from there you can say g of x is e power x. Right, so now the substitution is, instead of u of x, we will bring in new variable, which is v. V as u of x. So once we bring in this, so then dv will simply be u prime of x dx, right? And u prime of x is 2 times of x minus 2 dx and dv. I want x minus 2 into dx, so this will be dv by 2 is equals to x minus 2 dx. Okay, so now we got this x minus 2 into dx as dv by 2 in terms of v dv, and we have everything else sorted. So this will just be x minus 2 into dx will simply be dv by 2, and this will be e power x square minus 4x will be e power v. right? And the limits also we have to compute. And when u is 0, we'll have limits to be 5, right? So v is x square minus 4x plus 5. That is what u of x is. So from here, the lower limit of x is 0. So that means the limit of v will be 0 square minus 4 into 0 plus 5, which is 5. Okay. And when x is 1, we have the limit to be 1 minus 4 plus 5, right? So which is 6 minus 4, which is 2. V comes out to be 2. And if I substitute the limits, I'll have 5 to 2, right? And we have e power v dv. And look at the integrals carefully. So what do I mean by integrating e power v dv, and lower limit is 5 and upper limit is 2? Does that make any sense? So we have e power v, okay, and we have 5, and we have 2. Okay, so we are not integrating from 2 to 5. We are integrating it from 5 to 2. What will it happen? Any guesses from anyone? Integral. Is this a valid? My question is this a valid representation? This one.
Area seem to be equal, but I think we can run on the graph in reverse.
Yes, sir.
When we graph, what happens? Graph will be
In reverse order, runs in reverse.
reverse. What is the mathematical representation of reverse?
Minus sign.
Minus.
Yeah, it will become minus. You can also plot this. Maybe after this example, I will show you. Okay, so not x minus 2. Just give me a minute. I will share that screen for you guys. Just a second. Let me stop this sharing. Okay, let us compute this and then compare it. Okay, so if I not blindly, if I substitute the limits, I'll get e power v, and the limits are 2 and 5. And this will be e square minus e power 5. And if you compute e square minus e power 5, it comes out to be negative. Right? So negative something, because e square is lesser than e power 5. Let me also show you guys. I hope my Desmo screen is visible, right? Is this visible?
Yes, sir.
Yeah. So you can see the value comes out to be blurry.
Sir, I can see only your profile picture.
Oh, is that so?
Now it's okay, sir.
No, sir, it's Desmos is visible.
Desmos is visible, no? Let
Yes, sir.
Yes,
me
sir.
zoom it for you guys a bit.
Yes, sir.
Okay. Okay, so you can see clearly minus 70.5120. So that is nearly e square, not nearly, it is exactly. Okay, did we miss something? I think there is some half in the picture,
Divide by
no?
2, sir.
Yeah,
Divided
divide by
by 2.
2.
Yes, sir.
So there is half. So you can see exactly the integral will be equals to minus 70.51, because if you plot this curve, no, you see how the curve looks, green curve, and we are trying to compute the integral from 0 to minus 1, and 0 to minus 1 you can clearly see, sorry, 0 to 1 you can clearly see the curve is in the downside of x-axis, and if you compute the area for this, it gives us a negative area, right? So that is why we are getting such expressions. But if you ask me, can I represent it in that way? Then the answer is wrong. You cannot represent it in that way. Let me show you the actual representation. So if the lower limit is higher than the upper limit, then what we do is we take a negative sign. I hope my new
Yes,
our
sir. It's
old
visible.
screen is now back. Right. So this is not mathematically correct. Instead, if our lower limit is higher and upper limit is smaller, then what we write is we take a minus outside and make the lower limit to be upper limit and upper limit to be the lower limit. So what we do is instead you take the minus outside and we integrate it from 2 to 5 e power v dv. So it's not e power v dv actually. So this is dv by 2. So we have by 2. Okay, so there is by 2 by 2. So this will be the answer. Okay, so this is the actual or mathematical way to represent whenever you encounter these kind of situations. Okay, so where your lower limit is higher and upper limit is smaller. All right, so this makes sense. And when you compute also, you'll eventually reach this value only. So even if you compute now from here, you'll get e square minus e power 5 by 2 only. But there are some rules and restrictions, right? So you should follow. Okay, so that is about integration by substitution. And as I mentioned, integration by substitution will not work for any function f of x. Okay, so that need to be in proper format in this way. Only then we can do. Or there are some more examples where you can use substitution and convert this into a known form. So if you see this example, it's very hard to get u of t. But what we can do is we will not usually when we do problems, no, we will not go behind this g of t or u of t. What we do is what kind of function I can replace it with a variable, another variable. I'll have some nice, very well-known functions. So here in this problem, if you carefully observe, if I substitute some y to be t plus 1. Okay, so what happens by substituting y to be t plus 1? If I take dy, it will just simply be dt, right? And t will be y minus 1 because y is t plus 1, right? And we have t covered, and square root of, sorry, why I'm writing like this? This side I should write. No? So y minus 1 will be t, and square root of y is square root of t plus 1. right? So dt, t and square root of t plus 1 are the expressions here. And they are going to be replaced by dy y minus 1 square root y. And along with this, we have to compute the limits also. So y is t plus 1. So when t is 0, y will be 1. When t is 5, y will be 6. So now the new limits are 1 to 6. So if I do the substitutions along with the limits, right, so this will be 1 to 6. Now t is y minus 1, and then square root t plus 1 is root y, and then this is dt is dy. Now what this became is 1 to 6. This will be y power 3 by 2 minus y power 1 by 2 dy. And we know y power a is antiderivative, right? So we can use that. And also it is difference between two functions. I can split and do the integral and finally get the value. So the antiderivative for y power 3 by 2 will be y power 3 by 2 plus 1 by 3 by 2 plus 1, which is 5 by 2. Minus, for this it will be y power half plus 1 divided by half plus 1, which is 3 by 2. And the limits are 6 and 1. So all you have to do is substitute 6 and then subtract by substituting 1. Okay, so just be careful with signs. That's it. So you can compute and you can check. Okay. All right. Is this okay?
Yes, sir.
All right. Great. So now I think we will come to the final part of week 8, which is the last technique, which is integration by parts. Okay. As I said, if you have two functions, okay, so if your f of x can be split it into two functions, u of x, v of x, dx. Okay, so if you are integrating it from, let's say, a to b, this you can write this as, let me be very careful about this. So u of x, you can take the integral a to b v of x dx. Okay, minus whole integral a to b. This is, you compute the integral and limits will be b to a, and then minus integral a to b. You compute the derivative of this, and then you compute integral of this dx. Okay, so slightly complicated. It looks complicated, but let us simplify this. Okay, so what we do is, what can we do? Let us come from antiderivatives. Okay, so you have some, let's say you have some function f of x, which is u of x into u prime of x. Okay, or in other words, u dv. Okay, first function, derivative of the second function. Now, for this function, its antiderivative f of x will be u of x v of x. Okay, it will just simply be u of x v of x minus the antiderivative of u prime v of x. So you have u prime v, another function, its antiderivative, and should be subtracted from u of x v of x. And proof, I think you can do it real quick. You compute f prime of x, you will end up getting f of x. Okay, so here this will be, this you can write this as u v, right? So u of x v of x is u v minus antiderivative is basically integral u prime is dv and v. So v du. Okay, so this came from the product rule. So we have this f of x into g of x, right? And its derivative is f prime x gx plus g prime x fx, right? So if you see here, let's use u and v, which will be much more clear. So u of x v of x derivative is u prime of x v of x and v prime of x into u of x, correct? So when you have this f of x, which is u of x into v prime of x, this will actually be u of x v of x whole derivative minus u prime x. So this one, this is basically u of x v of x whole derivative minus u's derivative into v of x, right? So this is this, and if you are looking for the antiderivative, right? If you are looking for the antiderivative, then if I take the antiderivative of this derivative, you will get u of x v of x, right? And this antiderivative will be integral u prime x vx, right? So this is what I wrote. So this is integral f of x, which is capital F, which will be u v minus integral v du. Okay, and yeah, this is v u dv. Okay, so proof comes from that derivatives property, and all we need here is, there are few things we need. Okay, so firstly we bypart this u of x and v of x. Okay, so we separate this, and then what you do is you drop the limits. Okay, it's called indefinite integral, right? So when you drop the limits of integral, I think I missed it, but I hope you all know this. Can I assume that? So till now we saw definite integrals, no, with limits a to b f of x dx. So when I drop the limits, it will just be f of x dx, and this is called the indefinite integral. Okay, which is what we are trying to compute till now, the antiderivative. Okay, this is the antiderivative, which is without limits. Okay, and what we do is, if we want u of x v of x dx, then what we do is, firstly we drop the limits for the first step. You drop the limits, then you take u of x integration of v of x dx. Okay, so the first function, you take it as it is and integrate the second function, minus you take the integral and then take the derivative of the first function and then integrate the second function dx. Okay, so this is what we have to do. We have to compute this integral vx dx. Okay, so in both the expression, both the terms, we have that. In the first term, we have u of x. In the second term, we have to take the derivative of u. Okay, and then what happens is, here we have only a single function and we know how to compute this integral of v of x. So that is why we break this down, f of x into u of x into v of x, where I know the integral of v of x. That is how you should break. So once we know this, we can compute these two. And when you do this u prime of x, we will make sure that the expression that results when I compute the derivative of u of x is much simpler compared to u of x. Okay, so that is how we divide this u of x and v of x. If not, we can't use this by parts, right? So why we are using, again going back, why we are using this technique is to simplify the computation, not to complicate the computation. So for that, when we are choosing this u of x and v of x instead of f of x, we have to be really very careful how we choose u of x and v of x. Firstly, we should know the integral of v of x. And secondly, the u of x term that we are going to choose, when I take the derivative of it, the resultant should not be complicated. Complicated, I mean, it should not grow or it should not look bigger or complex than u of x. If it is looking in that way, then this will again become complicated. And there is no point of using this by parts. Okay, and with the well-known standard functions, there is a nice way to remember this, how to choose u of x and v of x. I think this also you guys know. Have you guys heard of islate anytime?
Yes, sir.
So what is I?
Inverse.
Yeah, inverse function.
Inverse functions.
L is logarithmic functions.
Logarithm.
A is algebraic.
Algebraic.
T is trigonometric.
Trigonometry.
And finally, E is
Exponential.
Exponential.
So this order is chosen for u of x, not v of x. So if you have inverse and logarithmic both as u of x and v of x, you should choose u of x to be inverse function, right? So that is why exponential stays at last, because if you choose exponential to be your u of x, then if you derivate u of x, you will still have that exponential. So it will not go out, right? So this is used to decide which one to be u of x. So whichever comes first, that will be u of x, and the later one will be the v of x. Okay. So yeah, so this is some nice way to remember the by parts. All right, so let's do some problems. Okay, so let's do with indefinite integrals only. We don't really go with definite. We can do definite also. All we have to do is to substitute limits. That's it. Let's do some examples. The very first example, let's take this integral x square into e power x dx. Okay, so we have x square and e power x. This is one function and this is another function, and we can see this is algebraic and that is exponential. So this is u of x and this is v of x. Now this will be equal to, I will have to take u of x as it is, multiply it with integral of v of x dx minus, I'll take the integral of u prime of x, integral of v of x dx. Right, if I do that, u of x is x square and then integral of e power x dx minus integral, the derivative of x square is 2x and integral e power x dx. Now we have x square into integral of e power x is e power x minus integral of 2x into e power x dx. Right, again, if you see, I can pull out the 2, the properties we learned, no? So 2, the constant you can pull out, and this will be x into e power x dx. So again, here also we have two functions, x and e power x. Right, again we can use the by parts. So x square into e power x minus 2. Now this integral, again I will take this as u of x and this as v of x. If I take it in that way, that this will be x into integral e power x, which will be e power x minus integral x derivative, which is 1, into e power x dx. Right, so now it will be x square e power x minus 2 x into e power x minus integral e power x is e power x. If you simplify, x square into e power x minus 2x into e power x plus 2 into e power x. If you pull out e power x common, we'll have e power x into x square minus 2x plus 2. So this will be the integral of x square into e power x dx. Right, so in this way, we can compute the integrals of the unknown integrand. So x square e power x we don't know till now, but we can use this integration by parts and compute the integral of it. Therefore, this will be the antiderivative, and you will add, at last you will add plus c if it is an indefinite integral. If it has limits, you substitute the limits. The upper limit you will substitute minus the lower limit. Okay, so that's integration by parts. Okay, I know you would have studied all these things. You just have to recall them, practice more problems, so that you will get a good grip on the formula. As well as if you forgot the formula, we won't forget this derivative formula. No, derivative formula is easy to remember compared to integration by parts. So when you remember this, you can actually derive. It will take some time, but you can derive it in the exam also. Whereas if you practice more problems, no, even it will, the formula you will get by hearted. It will get by hearted. Okay, so for these kind of concepts, you should practice more problems than sit and understand theory. Okay, so tomorrow is the third session for week 8, where again TA will discuss some plenty of problems related to week 8. Again, tomorrow also you'll get a hands-on experience on the week 8 concepts. Okay, and day after tomorrow we have revision session from 4 to 6, where we are going to cover week 5 and 6. Okay, so please make sure if you are available, please make sure you attend in person. Sorry, not in person. You attend the live session at that time. If you are not available, at least go back, visit in YouTube. Okay, and Friday we have the second session where we revise week 7 and 8. And Friday is the deadline for mock. So I forgot to mention this. So mock has been released. Please do check. Okay, so we have released the mock today evening. Please check the portal. Mock has been released, and the deadline for the mock is before the final revision session. That is Friday 10 a.m. will be the deadline for mock. Okay, so all I suggest is if you have finished watching the content till week 8, please do time yourself and solve mock and try to attend the revision sessions.
Sir, once
Yes.
can you make check the deadline, sir? Because before quiz one, the mock, like the time was given on the last revision session only, but it was given till like midnight.
Yeah. Okay, I will just check it. Yeah, this may happen. Just a second.
Sir, what will be the syllabus for Q2 exam?
Syllabus will be from week 5 to 8. Okay. It is 10 IST, 10 a.m.
Yes, sir.
Okay.
Okay, so 1st August, 10 a.m. is the deadline. All right. So you have 5 days if you count today also. So if you finished watching the lectures, all the assignments, submitted graded assignment week 8, I sincerely request you guys to solve the mock and then attend the revision sessions. And then if you still have time, practice the concepts once more. Okay. So I hope I have covered all the things of week 8. And that's all for today. We'll meet on Wednesday. Okay, so yeah, I will upload this PDFs.
Sir,
Yeah.
so week 7 and week 8 practice assignment solution and slides are not available in supplementary content.
Week 7 and 8.
Yes, sir.
Okay, I'll remind her once again. I have asked her to upload, the team members to upload. Let me check.
Okay, sir.
Okay. So anything else is pending from our side? Like we have released the mock, we have released the solutions, I suppose. I'll check on the this assignment solutions. And I think that's all, I guess. Yeah, Riemann sum is the heart of calculus, the heart of integration.
Sir, I have doubt in few portions related to activity question. Shall we discuss now?
Yeah, you can ask.
Sir, from 8.5, the last question.
8.5. Okay. So this is integral 0 to 4 e power x plus 5 divided by e power x plus 5x plus 1 whole square dx. Right? Is this the question?
Yes, sir, I did, but I get a different answer. And I
Different answer.
check. Yeah.
Okay, maybe I'll quickly do this. So I'll just substitute t is equals to e power x plus 5x plus 1. Right? So if I do this substitution, then let me compute the limits. When x is 0, the limits are limit will be 2 because e power 0 plus 5 times 0 plus 1 is 2. And when x is 4, the limit will be
e to power 4 plus 21.
e to the power 4 plus 21. Okay. So then this will simply be 2 to e power 4 plus 21. E power x plus 5 dx will be dt divided by
T
t
square
square. And t square antiderivative is
minus 1 by t.
minus 1 by t. Oh,
Yes, sir.
because
T to power minus 2.
t power minus 2 plus 1 divided by minus 2 plus 1. So it will be minus 1 by t. And the limits are e power 4 plus 21 and 2. Okay.
There is no option related to it.
Okay, so e power 4 plus. So what is the solution given? 1 by 6 minus 1 by e power 4 plus 5. Are we correct? I hope we are doing correct, no? 1 by t.
Options are incorrect, sir. I think
Oh,
so.
options are incorrect. But whatever we did is correct, no? I'm worried about are we doing any mistake?
I don't think so, sir.
This is there. This is power 4 plus 6. What if it is plus 6? Plus 5. Okay. So it should have been for x plus x. Hmm. Okay. This should have been minus 5x. Huh? No, even minus 5x is not going to work. Okay, I think it's incorrect. Something I think there is some mistake in it. Let me check and update it. Okay.
What mistake, sir?
Like I think it is something like e power x plus 5. It is like this.
We are just modifying the question now, no?
Or I think this is correct. So this is correct. 5x plus 1. Instead of 4, it should have been 1. Okay, if it is 1, what will happen? Again, here also it should be something like e power x plus 5. Now things will be much. So we are doing reverse engineering now.
Yes, sir.
So e power 4, when x is 1, this will, when it will be e only, no? Why e power 4 comes? When x is integrated to 1. Okay, leave it. So there is some mistake.
Sir, there is a one more question. Same situation is happening there.
Which
It's
one?
4.2. The previous activity question 4.2.
8.4, no?
Like
8.2 question. 8.4 question.
4.2, sir. Activity quotient 4.2.
4.2 is week 4, no? Yeah. Rest
Yes,
of
sir.
you
Week
can
4.
leave. Sorry. Week 4 you are asking.
Yes, sir. Week 4.
Okay. Others, if you don't have any doubts or you are clear about this, you can leave. Thanks all for joining and have a great day. Okay, question 2. 4.2, question 4, no?
Question number 2 from the week 4.
Okay, week 4,
Sorry.
active. Yeah, I'm not able to understand which. You are referring to week 4, is it?